Alright, welcome everybody. So indeed, the subject of my talk is security type aerodynamic management and work with a master student of mine, Jurriaan Weijers, now in Tübingen, and Stefan, Holdermans, who is a former PhD student of mine. So the slogan of the static analyst is actually typically bigger, faster, more. I also like to do that kind of thing, and type systems more powerful, being able to handle bigger, more complex languages. But it's also a fact that complicated languages are difficult to communicate about, particularly when people start to make mistakes. You can actually tell because there's hardly any work on improving type error for languages like C, C++, or Java. But there's a whole bunch of work for higher order languages. But most of that is restricted to the polymorphic lambda calculus. Yeah, so there's a whole history of that. Surprisingly enough, other validating analysis like Kennedy's dimension analysis or security analysis that I want to talk about today, there's been no work on improving type diagnosis in case inconsistencies show up. And as I will show you today, there are differences. So what is a security analysis? Well, this is a particular type of security type system that is imposed on, in this case, a functional language to ensure that programs preserve confidentiality. But what does that mean? Well, the bottom line is that if you have highly confidential values, you don't want to see them printed on a lowly confidential printer or sent to a lowly confidential screen. And formally that means that typically you associate either low, L, low with values or high with values, where high in relation says that this is less secure than throughout the talk I've used L and H as examples, so low confidentiality and high confidentiality, but if you want to, you can impose any letters, whatever, on your securities, and it will also work for that. So this is an example of a program. You see here a conditional. You see the function show low, that is meant to show low values, and what I pass into it is actually the value of high confidentiality, so you would expect the compiler to complain when I compile this program. You might wonder, why on earth is there a highly confidential boolean coming out if the if and the else and the then part are both lowly confidential? Well, the reason is, and this is actually why this analysis is different from the intrinsic type system, is because it's guarded by a highly confidential boolean. Note that if you want to have a language which is what they call a non-interference property, so it's very nicely well behaved, you cannot write real programs in it. Basically anything that you ever do with a highly confidential variable will for the rest of its life stay highly confidential. So typically in a language like that, to be practical, you need things like declassified, which is like an unsafe before IO that says, believe me, I really want this L value to become a high value. This high value to become an L value. So that you can actually, for example, if somebody logs in, you use a highly classified password file, but you still want to tell somebody you successfully logged in or not, irrespective of the fact that he was actually allowed in. So yeah, but we won't see much of that. So what do we do with a security type system? Well, what I usually do, I implement it or define it as a non-standard type system, or what other people call a type and effect system. What happens there is you have annotations on top of the underlying Hindley-Milner type system, for example. Now, security analysis is an instance of what people call a dependency analysis. There's a paper by Abadi, well worth reading, that shows that a lot of analyses, among security analysis, but also slicing and binding type analysis, are dependency analysis. And because of that, because the intrinsic type system is not such an analysis, there are differences. Now, the type system we define in the paper is state-of-the-art, so it has subperfecting, it's polyvariant, and the underlying language is polymorphic. And just to show you a little bit what is an annotating type, basically with an annotating type, you take the types that you're used to, like function types and ints and bools, and you add annotations to them. So there's to it. In this case, if you take an int, you add an annotation phi to it, and this phi will typically be this H or this L, saying this is a highly confidential int or a low confidential int. You do the same thing with a bool, with lists, where of course the element type also has this annotation. And so on. Now the language supports lists and tuples, recursions, and these protect and declassify that are particular for security analysis. So just to show you a few type rules, and this also allows me to show in what way this analysis diverges from the usual Hindley-Milner rules that you might hopefully be familiar with. Otherwise I guess you've worked thoroughly by now. So this is a conditional. What does it make? Conditional is well typed if the expression that you use here for the condition is a bool and the types of the then and else part coincide. That's why I have the towels here. But in this case, we also have annotations on these types. So this bool has some annotation. I don't know what it is when I write down this type bool for a particular program. I hope to be able to discover whether it's an H or an L. Yeah? So this guy should be H or L, this might be H or L, and this might be H or L. And then the confidentiality of the if then else is the join over those. Basically meaning that if either one of these three is highly confidential, then the whole Boolean expression is highly confidential. Another case important here is the head. So if I have a list, and this list has a certain confidentiality phi, and the elements of the list have a certain confidentiality phi 1, then the confidentiality of the first element of that list is maybe surprisingly the combination of the two. Now you might wonder why is that? Why if I take out something out of a list, why is the confidentiality of the list important here? Well, because if you can perform the head, it gives you information about the structure of the list. If it's successful, you know the list was not empty. So, if the structure of the list is highly confidentiality, the result of the head is also highly confidential, even if the values in the list are lowly confidential. So, what is our approach in improving type error diagnosis in case we are not able, by some algorithm, to find out that all the H's and L's are used consistently within the program? Well, the first thing we do is we transform, we massage the type rules a little bit to make them constraint-based. I'll show that in a minute. If you have constraints, and these constraints are typically only about the securities, not about the underlying types like the ints or the bools. We compute them in the Henry-Milner style. And then we take these constraints about the securities and we solve them by fixed point iteration, the worklist algorithm or something. Now, of course, if we do that and we find that they're consistent, then we're done and happy. But our work really starts if they're not consistent. What we then do is we compute a security type error slice. So this is inspired by the work of Hage and Wells. What happens, if you look at all your constraints, there's an algorithm that will allow you to decide what is the minimal unsatisfiable set of constraints. Meaning that if you want to resolve the issue, you have to touch at least a part of the program that generates the constraint that makes it unsatisfiable. In other words, the constraints that are not out in that slice, outside the slice, you should never mention them in your type error diagnosis. So it's kind of like a soundness property of your type error diagnosis. Don't mention anything outside the slice. That would be stupid. And then the final part is that because slices can be rather big, they also do not tell you, they just say, okay, these are the program points that contribute to the mistake. They don't give you any hint what might be wrong. They don't suggest fixes, for example. So it's a good approximation. As a first approximation, when we go on and we apply various heuristics to the slice to further narrow down the locations that might have a likely cause, or to suggest fixes for the mistakes. And then based on that information, the constraints that are basically left after we do that, and the heuristics that we used to further narrow it down or to find suggestions for fixes, we use that information to generate what we hope to be a to-the-point error precision. So first, massaging the constraints. The type system is implemented and solving a set of constraints, and these are the kind of constraints you see. For example, some expression to which we associated some confidentiality beta is supposed to be under H. Well, actually, all the constraints, all the confidentialities lie under the top of the lattice, which is H. So you might consider this to be typology, and typically when we solve this, we just throw it away because it will always be true. Another one is that says that H is below L, I is below low. This is not allowed. So this signifies an inconsistency, and the alarm bells start ringing. Some of these constraints simply say that I am at least as confidential as you. And most of the constraints actually are of this kind. And this just propagates confidentiality. Of course, we can only verify that this is whether we satisfy this or not when we know something more about beta 1 and beta 2, and this is exactly what the fixed point iteration aims to discover. So, we take our rules now and we start to refactor them a bit, rewriting them in a style that uses constraints, like this. So, the fact that I say here that the annotation on the tower is a join over these three basically means introduce a new placeholder phi there is that whatever I find for the Boolean, for phi 1, for the then part, and for the else bar, kind of push up the confidentiality of the complete condition. Yeah? So if one of these three is H, then phi also has to be H. This is exactly in this case the behavior that I want. If all three are L, then I choose L.
But there you only capture it's an upper bound, not the least upper bound.
No, but I don't know because that's because all the rules I have here, they're already towards the implementation, so I've already included the sub-effector. I don't have to choose the best one. Maybe depending on its context, it might be better to have a worse one to make it right for the next level up. But of course, because I use fixed point iteration, it will find the least fixed point if I run it. But I don't have to enforce it to be the least fixed point. The algorithm will do it. And that's because the least fixed point, if you choose equalities or inequalities, it's the same thing. The least fixed points are the same. Yeah? So this characterizes sound solutions. And the least fixed point among them is the best solution. And I will find it, at least the worklist algorithm will find it if it's okay, so security type slicing, I kind of told you this already. So there's two papers actually, Hage, Wells, and Stuckey et al. This is a type-based way, this is an algorithmic way, and we use the algorithmic version to compute all the locations in the program that generate constraints that contribute to the inconsistency. It's a short algorithm, but if you read it, it doesn't explain itself, so if you want to understand it, you really have to run it by hand, and then, well, everything will be clear. Because that's how it happened to me. Okay, so then step 2, which to me is the more interesting, because this is where we kind of have to develop new heuristics to be able to deal with the differences between an intrinsic type system of like Milner and a security type system that we look at here. Is that so step 1 gives us a set of constraints, but it might be large, and maybe we want to have a more precise diagnostics. So there is a risk here. Once you try to be more precise, you give a hint saying, well, maybe this is what you did. It's possible that you are wrong. You can always find cases where you are wrong. The goal is to be right most of the time, or many of the times. At least in my opinion. Yeah, but there is always the risk of being wrong, because you start to guess at the intentions of the program. All right, so we've identified 4 classes of heuristics. So there are genetic heuristics that basically say, if I have a ton of evidence pointed to L, and one small piece of evidence pointed to H, I'm going to blame that H. And that's what we call the majority heuristic. This is old hat. Maybe even developed before I was born. Another one is to avoid irrefutable constraints. So actually, some constraints are just meant to propagate confidentialities. That the body of a let has the same confidentiality as the whole let is not something that you will want to blame the programmer about. And that's part of the fact that the value that you get from let is exactly the value that you get from its body. You cannot blame somebody for that. So these are what we call irrefutable constraints, and you never want to generate an error message based on an irrefutable constraint, so you have to remove them explicitly, because the slice will contain them. Another one is the propagation heuristics. If you have a value of high confidentiality, you pass it to the identity function, you get a value of high confidentiality. If you pass that to something that takes a low confidentiality value, you don't want to blame the identity function. You have no reason, because you might have passed it through hundreds of identity functions. Which one of the 100 are you going to blame? So functions that pass on values, at least do not change these confidentialities, leave them alone. So that's what we call the propagation heuristic. Don't blame these guys. Then there are a few security-specific heuristics, and we'll talk about them in the paper, but I'll spend some more time on the dependency analysis-specific heuristics. So, security type systems are not often used by programmers, and for example, if you start to use them, you are probably used to Milner behavior. So, if there's something in which the security type system diverges from the intrinsic type system, that is particularly a place where you will start to make mistakes. Your or my misunderstanding. So the intuitions of the intrinsic type system do not always carry over. So what we did is we simply took the Milner type system and the security type system, and we looked to see when do we have the same types, and are the annotations different, and when are the annotations different, and do we have the same types? The other way around. And for each of these differences, we implemented the heuristic to discover whether, and this misunderstanding on the part of the programmer does explain the type inconsistency. So for example, here I've modified it. So here I have a nice bool L, which of course fits very well into this alpha L, but there's an inconsistency because this should have been an H, because I have to take the join of this guy, and that guy. But possibly the person who programmed this only feels that the value of the then and the else part flow to the result of the conditional. He doesn't see the bool flowing to the result. Actually, it's not this bool that flows there. It's these bools that flow there. And then you might forget that knowing the result of this conditional, you can actually find out information about what the value of this conditional is. If you get true out, you know that this boolean was actually true. Otherwise, you would have never gotten that out. So this is typical for the dependency analysis. You can find out things about how something was computed, particularly for the counterflow and the guards, based on the outcomes of your computation. And this is forbidden by the security type system. So the fact that you see this phi 1 showing up here is particular for this analysis, and is different from the other analysis, and this is why we define heuristics. So we have a number of these cases. Also for the head case, that you reveal information about the structure of the list, shown by this join here. This is different from the intrinsic type system. Now, I'm going to skip this. So this is a more sizable example, just to show you what kind of error message you get out. There can be something improved. The point is that we can generate these error messages saying to the programmer, look, you have a head here of a list, and this list has a nil, which is a high, so the whole list, the structure of the list is high. So the head of this list gives you that high, because the head takes the element annotation and joins it with the annotation of the list structure. So this is a high, this is a low value, that's a low value, and we may think that this is a low value, and then it's correct to pass this value into the log, which expects a low value. But because this is a high, it won't work, and actually this rule explains that head ZL generates a high with a confidential value, and in the end it doesn't, it clashes with whatever we want to pass to log, because we use it in this conditional construction. Okay, there's another example of the majority. Yeah, so you have 1, 2, 3, 4, 5. 5 is high, the rest is low. And here you see, for example, that we actually blame the 5 because it's the only one that is high. And this is another example of a propagation of the majority. So, almost done. This is a summary. The superficial, I tried to give you a superficial impression of how to design a security analysis as a type and effect system. Just a few rules, of course, the rest is in the paper. I've described 4 classes of heuristics to specialize the type error diagnosis and give you a few examples. As far as we know, this is the first paper to combine slicing with the heuristic approach. And of course, the paper contains many more details, which leads me to how to sell this paper to IFL. So the paper in its current form is 12 pages ACM style, and if you include the algorithm, so our variant of algorithm W, that has all the word list and the blah 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 blah, it's 19 pages ACM style. And that won't fit. Probably we can save a few pages here, but 15 or 16 pages LNCS style is about, it's about 9 pages ACM style. So I was wondering, maybe during the discussion, or if you're a receipt member afterwards, for example, what do you think is the best thing to include? What can I keep out of it? Keep out of the paper so that you won't blame me afterwards. You should have put that in. That's easy. So that's kind of the discussion I would like to generate here. And the important thing is that...
we won't write your paper.
Sorry?
We won't write your paper.
No, I'll write it. If you tell me what to write, I'll do it.
Write a good one.
Qualify good.
A short one.
Okay,
that's it.
Speaker. Any questions or suggestions? No. You disappoint. Come on, people.
So where do you draw the examples from? Are they sort of...
Well, we constructed them. Because one of the problems here, look, I also did this thing in 2006 at IFL, but then the nice thing was I had 60,000 helium programs with type and I think about 25% of these had type errors. So when I defined heuristics for that, I could measure at least, for example, how often heuristics were employed, how often they were instrumental in deciding on a particular constraint. My problem here is if there aren't any users, and it could be a problem biting its own tail, because it might be that people think, well, I'm not going to implement or use a programming language with security type system because the errors are unreadable. And so they will never get anywhere.
But the errors here are presumably better, right? For the same reason that
well, better than what?
Yeah.
So you can compare against Poitier's camel implementation because our analysis is very much like it. I mean, we are better because the only thing he says is that H shouldn't be under L. But that's also because he didn't care about it. Yeah, so it's what is better than, yeah. But then still, there are differences between our languages and theirs. We've also looked at Rousseau and Klaassen, Hughes, embedded library. But there, for example, you already have the issue that the errors are confounded. If you make a mistake in your normal types, you will have the security annotations among them. If you make an error in the security annotation, you will have the usual types, big types among them. So the comparison is very hard to make. There certainly are not any benchmarks. And there aren't any users. The only thing I could think of is simply come up with a lot of examples, but then you have the problem, you know, where do you put this in the paper?
Okay. Yeah.
You also talked about typing security primitives such as encryption and decryption. So if you encrypt something which is
Oh, you can in your gamma you can put a function that you say is called encrypt, in which you pass in the value of low and out comes the value of high confidentiality. But that's only you can do that by just passing that into the environment. That's easy. Of course, I only look at confidentiality. It turns out there are dozens of other forms of security analysis that are way more complicated than this one, but it's manageable.
Perfect, thank you.